Okay, everyone. Thank you today for attending this webinar. I'm very happy to be hosting today the third Beicip-Franlab expert talk. Today we'll be discussing about the Orphan Basin, offshore Canada, and then we'll discuss a lot about the resource assessment using the forest stratigraphic and petroleum system models. And you'll be featuring also different types of benefits and how can we couple GNG concepts with numerical models and what can we bring as outcome out of these studies. So of course today I'm introducing to you Dr. Erwan Le Guerrouet and Paul Germano, who are two experts in Beicip-Franlab. So Erwan has more than 15 years of experience. He had the structural and stratigraphic interpretation team in Beicip-Franlab. And Dr. Paul Germano also has more than 14 years of experience in sedimentology, sequence stratigraphy, and seismic stratigraphy. Paul has developed also a wide experience in forest stratigraphic modeling and petroleum system modeling solutions and resource assessment that we will be discussing today. And myself, I'm Nicolas Hawi. I'm a petroleum system analyst also in Beicip-Franlab. So just a small couple of guidelines for you guys. So all of you are muted, so please keep the mute on. If you have any questions, you have the toggle up there to the question toggle. So you can write us the question and we'll be answering it to you by the end of the presentation. And then I just want to tell you also that the video is recorded. So it will be also available on our YouTube channel. So for those who did not have time or for future interest, don't hesitate to get to our YouTube channel. Erwan, to you.
Yes, thank you, Nicolas. Good morning, everyone. Good morning and good afternoon for the ones on the other side of the Atlantic today. Thank you for joining us. We are delighted to have you today with us. I guess we're all here because we are interested in resource assessment and how to efficiently evaluate them. Well, us at Beicip-Franlab, we do provide independent, cutting-edge solutions and numerical tools to evaluate and risk potential resources. Today, we propose you to discuss what we have done here in that very example of Newfoundland, Canada, and browse you through the key steps that allowed us to confidently announce the resources that were undisclosed a few weeks ago. So we're going to talk about GNG concepts and integration into a forward stratigraphic model that will then pass to a petroleum system model and allowing us to calculate resources. So first, a little bit of history. Since 2010, Beicip has conducted numerous independent integrated exploration studies for areas subject to upcoming license rounds. That was done in the entire eastern Canada, from Nova Scotia to Newfoundland and Labrador. Such evaluation are based on software exploration developed in-house. There's a double objective attached to these assessments. First one is to provide the oil and gas companies with a public independent report ahead of call for bids. And on the long run, it helps provincial governments to manage their offshore potential. Let's now focus more on what we've done within the offshore of Newfoundland. And I'll pass the floor to Paul for the next slides.
Thank you, Erwan. And thank you, Nicolas. So for 5 years now, in prevision of upcoming bidding rounds, as Erwan said, Nalcor Energy, which is the provincial energy corporation, engages Beicip-Franlab to conduct independent resource assessments of the offshore province. So out of those 5 years, Beicip-Franlab has built on those successive projects and gained an exclusive knowledge leading to a comprehensive understanding of the behavior of the petroleum system at regional scale. This year's resource assessment, which is a red square here, sits in between previous studies and shares a lot of aspects with them. Consequently, it benefits from that year-to-year understanding in terms of basin geodynamics, stratigraphic architecture, as well as the thermal and maturity history. And you've got here a nice example of the mapping of maturity at top Jurassic compiled from the successive petroleum system models for 5 years. Just to show you on this slide, you will find some details on how to access to all the assessment we released with Nalcor. Another word on the impact we like to think we contributed to is on the world commitment that companies made, which represents around $3 billion in 4 bid rounds. So this year, the study area is this one. It includes 6 new parcels open for the November call for bid. Just a few words on the broad geological context. This area lies within the Orphan Basin, which was subject to 2 consecutive episodes of rifting. The first one occurred in the late Jurassic, early Cretaceous, and is related to the opening between North America and Iberia. It is followed by a second episode that occurred during the early Cretaceous and related to the separation now between North America and Eurasia. So polyphasic history linked with the Atlantic opening at regional scale, and that generated complex structures at local scale. And among those structures, all of the structures, a few of them were drilled in the past 15 years. So luckily, 4 of those wells are within the study area, but unfortunately, they are all dry. And this is one of the key points we have to explain. It is to note that these wells were drilled before the modern seismic acquisition, and at this time, the strategy for the drill seemed to be the same, targeting a massive structural eye. More than a decade has passed now, and we've got now, in addition to the wells, a new data set which consists in a fantastic 3D seismic volume set. And we'd like to thank TGS, PGS, and Nalcor for that. And cherry on the cake, that volume covers nearly the entire parcels of the studied area. So this is this high-resolution dataset that allows delivering some of the new interpretation and models that we present here. So how to take advantage of such data to deliver a consistent petroleum assessment? The workflow we propose consists in an original integrated work that has now been raised to a routine job within our teams in Beicip. It implies the systematic use of conceptual GNG modeling coupled to numerical for stratigraphic and petroleum system modeling solutions. So those modeling tools that you've got here are used to unravel the history of sedimentation and structuration, as well as the history of hydrocarbon maturation, migration, and entrapment. So I'm going now to detail the GNG analysis coupled with numerical for stratigraphic modeling, and Erwan after will move to the petroleum system modeling. So as I said, any numerical model requires preliminary concepts. So we've started with the combined analysis of the wells and the set of 3D, 2D seismic information in order to set the structural framework at first. It consisted in an exhaustive picking of the faults in relation with the timing of their activity and leading to the concept of the history of deformation from the local scale up to the big scale. Then a precise object-based mapping of the seismic was performed toward the whole area in order to highlight the sequence stratigraphic framework, the relation between sedimentation and complex deformation, and finally the successive depositional environments. And you can see that those depositional environments are both dressed up in representative 2D section and in 3D gross depositional environments map. So once having done this sequence stratigraphic framework, we did a time projection of our key regional section. Then key play elements are displayed on this kind of wheeler view, which is consequently turned into a representative stratigraphic chart of the area. Such a time chart facilitates the play definition, which has been defined as follows for the central Orphan region. So as you can see, 6 play intervals with 2 major ones that will be revealed by the following resource assessment. So having done this analytical job, we are able to tell a consistent story of the central Orphan area. The initial phase of rifting occurs during the mid-upper Jurassic. The active tectonic subsidence leads to the formation of very segmented systems of ores and grabens. The grabens are filled with clastic material produced by the erosion of neighboring ores. During the Chimeridian, as rift keeps opening, marine intrusion is suspected to start from the south. Shallow marine conditions prevail in the central and eastern grabens, with associated slope turbidites developing at their edges. At the same time, continental fluvio-alluvial systems remain active to the northwest. During Titonian, the rift opening continued propagating to the northwest, and marine conditions prevail toward the central and eastern region, except locally where some ores remain above sea level. The central rift graben are connecting, and wider basins are forming to the east. The stress regime drastically changes during early Cretaceous, when the main extension direction is shifted to northeast-southwest in shallow to open marine context. The connection with the open ocean also lead to eustatic influence, resulting in successive periods of transgression and regression. This rifting stages progressively decreases during the late Cretaceous, with continental breakup separating Newfoundland and Ireland. The differential of thermal subsidence between the eastern region and the west led to the increase of paleoslope around the central Orphan eye and the development of turbiditic systems flowing from the highs, such as the Orphan knoll to the north, down to the eastern and western sub-basins. Finally, during the Cenozoic, the basin evolved to a classical passive margin. The turbidites delivering clastic materials to the deep offshore, they are flowing from the western and southern Bonavista platform. Their flows are topographically constrained either by giant contoritic ridges growing up locally on the slope, or by remnant or topography. So once you get the GNG concepts, so now let's run and test them dynamically. So while performing a 3D forward stratigraphic modeling at this step of the workflow, first, to validate dynamically our concept on sedimentation, taking into account the interplay between sediment supply and accommodation history. Second, to provide a calibrated 3D, 4D geocube fed by various geological properties. Those properties can directly be injected in any geomodel for further geological property analysis, but it can also be directly used for play assessment and geological risk mapping. Note that we were able this year to simulate the deposition and preservation of organic rich material by using the Dionysos brand new modules. And last but not least, forward stratigraphic modeling allows testing different alternative scenarios of deposition if uncertain parameters are revealed by the conceptual model. If equiprobable scenarios of deposition are successfully calibrated to the dataset, it means that alternative geocubes can be provided for further petroleum system model. So let's have a look to the kind of geocube that have been extracted from the 2020 study. So I propose to visualize dynamically one of the final geocubes in a paleobathymetry view. As you can see, we can nicely reproduce the rift opening of the margin during the mid-upper Jurassic and the progressive onset of marine setting during Titonian. Then we follow up with the second phase of rifting in marine setting during lower Cretaceous. You can also observe the eustatic pulse of flooding and sea level drop once the basin is almost drowned and connected to the Proto-Atlantic, up to the early late Cretaceous and the onset of more passive margin state. So one of, as I said, the most powerful aspect of forward strat modeling is the ability to test dynamically alternative geological scenarios, see if we can calibrate all of them, and if yes, what is the impact on the distribution of the reservoirs, the seals, the carrier beds, and the organic rich material. This is what we performed in this study, where we decided to explore alternative realistic views to bring robustness into the assessment. The first hypothesis concerned the timing of the absolute sea level change in regards of a key geodynamical change affecting the basin. What we know from the GD mapping is that across the transition between the Kimmeridgian and the Tectonian, the Orphan geomorphology evolves drastically from constrained and segmented rifted mini-basins to more widely open rifted grabens. What we also know is that during this transition, the Eustacy records a significant sea level rise, which is associated worldwide to the deposition of one of the most prolific source rock ever. So the hypothesis here is about the synchronicity of those two parameters, geodynamics versus Eustacy, and the impact on the spatial distribution and richness of the source rock. The first case sees the geodynamic change happening while the eustatic signal starts to rise. The other one right after the rise. And what are the main effects? Scenario one is favorable to a rapid marine drowning of the system, which implies more oxic condition and, also, as a matter of fact, less preservation of organic rich intervals. In scenario two, because of the lesser impact of sea level rise, more restricted conditions remain in the subsiding but less connected grabens. This will favorize the preservation of richer organic matter clusters, but on more localized and smaller areas. The second hypothesis on uncertain parameters concerns the sediment mixture entering the basin. Is it sand-rich or sand-limited? Both hypotheses are simulated and calibrated to wells within the model, and results are showing that the significant variation in sand content are observable once we move away from the wells, and especially to the north. So finally, we end up with 4 alternative scenarios, all calibrated. Since they are geologically equiprobable, they were all used to set up the Petroleum system model and at the end considered for the sensitivity analysis of the resource assessment. Just notice that other hypotheses were tested, but since they are not honoring the data, they were discarded. So now let's discuss about the Petroleum system model and how we evaluated the resources. And I leave Erwan for the rest of the show.
Yeah, thanks, Bob. We move now to the Petroleum system model, and to do that, we use the classical Petroleum system model THEMIS flow that uses thermal, pressure, and maturity calibration, and we couple that model to the unique kinematic 2D Petroleum system model that it's called Kronos flow, and this model allows to properly balance a section before simulating it, and also to play with fault properties. So we'll talk more about it. One first thing is now that the first key step that we have to resolve for Petroleum system is to pass from the dinosaur's high-resolution grid to an upscale version that will be fitted for the THEMIS flow. So the dinosaur's grid is more than 1,300 layers. And how do we fit that to a Petroleum system? Obviously, we need to do some upscale. So this is the resulting upscale Petroleum system grid, where the main lithophases distribution is respected and the Petroleum system included. So I can go back and forth between the two grids, so you can have a feeling that the main architecture is respected there. And the important message is that these fasces, or the architecture is respected, and most importantly, the Petroleum system elements are all implemented into the geomodel. Source rock definition. So based on all the available data and the stratigraphic model that Paul has performed, we recognize several source rock levels. You have here the result of the source rock in the section view, and also on the side the paleogeographic maps associated with these deposits that give you a sense of the distribution of potential source rock. Few things. Two proven Titonian source rock. The lower one of the source rock is the lateral equivalent of the A-grade formation of the Jeanne Basin, because it shares the same kinetics. So there's debate about its exact age. It could be lower Titonian, upper Kimmeridgian. This is not very much important for us here. The important fact is that it is a proven source rock and with known kinetics. From Dionysius flow runs, there's a possible lower Kimmeridgian source rock that exists in the basin, and it was therefore included in some of our scenarios. Since it's a possible source rock, it wasn't accounted for in all scenarios. Another additional source rocks exists during the option. It's mostly proven by the log calculation. Its impact overall on the Petroleum system is weak because it's poorly mature due to a lack of burial. So a thermal model is built. It's based on the lithosphere condition associated to the rifting history and of the basin through time and space. So the model is calibrated, you can see the curve over here, to available temperature and vitrinite data at well. So there's not much data, of course, it's often the case in exploration studies, but the calibration here was good, and basically the model calibrated on the first go. Let's now see how the model behaves. This is the maturity expressed in terms of equivalent vitrinite reflection on the section above here. In the maps, you can see the different source rock levels. We clearly see that the Jurassic source rocks are now well within the oil and gas windows. The map below, allows to grasp the spatial extension of the maturity. One thing to note is that for the Egyptian level, the potential is in places where the buried of the Cenozoic platform is. So basically on the western side. So the added value of the model is to be able to track that maturity evolution through time as the basin gets buried. Something more interesting, with maturity comes transformation, expulsion, and eventually migration. So you have here the same section as before, showing the transformation ratio for the different source rock level. You can clearly see that on the side of both wells, down deep, the source rock have transformed and expelled. On the maps below, they show the timing at which a source rock has passed 25% of transformation ratio. So basically when it started to expel, you can notice that there are large-scale trends there from east to west, which is quite good news because it means that throughout the AOI we have different timing and different scenarios for oil and gas expulsion. So for Kimmeridgian, expulsion starts more in the Jurassic on that side, passing to early Cretaceous. Here it's more early Cretaceous to late Cretaceous, and so on. Then hydrocarbons migrated. On that 3D view, we can have an idea of a different drainage area, eventually leading to structural closures, here in purple. So the model tracks the masses of hydrocarbon reaching those locations. We computed all those masses for all the different scenarios, and obviously there were differences between the scenarios, but all the models that we did demonstrated a prolific petroleum system. So most importantly, now what happened at the dry well location? Well, that section over here highlight those two wells, one were here and one is over here. And so we're going to use that model in 2D to test the fall and the structural balancing to perfectly understand what happens at these two well locations during the basin burial. So there is the same section over here, so it's restored in time, and we are looking at the top Titonian age here. So this is using the software called ChronosFlow. All properties and calibration are extracted from the 3D model, And below here you have two seismic interpreted sections, obviously at present day, and they pass by the dry wells. So on those sections and on the well record, we can demonstrate that there's potential for reservoir and for seals at both well locations, and also in Great Barras Way there's a demonstrated source rock. So basically for those two dry wells, they could have been a success. Something went wrong where it should probably not have. So if we go back to the chronosphere section over here, so the faults are implemented as individual objects, and one can play with their properties. It can be either transparent, permeable, impermeable, or we can do combinations of the latest two. We'll come back to that. The section shows here the saturation on top of a mesh. So it's fairly faint. We don't see so much, but I'll walk you through it. So two key points here. At Great Barras Way in the Jurassic, the area is actually a depot center, and it explains why there's good source rock record up the well. Lona, the structure starts to rotate with the rifting, and very, very early migration and some saturation happens down deep the block. So it's very faint, it's here. We're going to see more of that. So now I'm moving up to top Valanginian. So obviously the extension, the rifting is continuing. On the Great Barras Way flanks, you can see that now, due to strike-slip motions, the flanks of the structure are collapsing, and the depot center is transforming into an actual trap. And on the side of the flank here, the first expulsion of organic matter happens. Migration also happens on the western side of the Lona structure as the block continues to rotate. Here's a view now during the action, so extensions still ongoing. So the flank of the Great Barras structure are finished now to collapse, and on the side of the flank, hydrocarbon concentrate into the reservoir levels, migrating upwards through the fault pattern. Migration happening on the western side of Lona eventually spill up to the surface as the Cretaceous seal is thin over there and undercompacted. This is a general case for the higher structure, poorly sealed by sufficient Cretaceous layers. The first migration were most of the time lost in those highest areas until the Cenozoic added some sufficient sealing capacities. Now we're at top Albian time, so hydrocarbon around Great Barras Way are concentrated down deep against fault that now prevent further migration. Eventually maybe a little leaking up to the surface. While in Lona, the flanks are now properly sealed with this additional late Cretaceous cover. We're now at top Cretaceous. Accumulations are concentrating throughout the section in the highs and most of the time against faults. It is very complicated to chart Lona, although on top of a nice structural high here on the 2D sections, is probably due to long distance migration from the mature area up to the apex of a 2D section. I'll come back to that fact a little bit later. Top Oligocene view, the accumulations are stuck here against down deep fault at Great Barras Way. In the central area, some leaking happens to the tertiary levels, and local highs or on Lona are actually concentrating quite well more and more hydrocarbons. Eventually, present day, things did not really change in Great Barras Way. All accumulations on trapped against faults. Around Lona, weak hydrocarbon saturation eventually here leaked into the tertiary. There's no accumulation at the well, and especially not in the Mesozoic. Well, it seems like the fault behavior is very important for the hydrocarbon migration, and well, let's see how important. We have run different scenarios with different fault behavior. As I said before, we've run the same section with transparent fault, with fully permeable fault, with fully impermeable fault, and even combination of the two depending on the geodynamic timing. And the idea was to test the impact of this fault on the hydrocarbon migration around this dry well. Well, it's difficult to get hydrocarbon up there. We have no favorable options that will allow that. And because two independent evidence pointing at the same thing is always better, here's some result that PGS was putting in the literature at the same time as we did the work. So honestly, we knew about it after the work, and And honestly, Nalcor kind of knew it was up before, and they really appreciated that we did a successful blind test with that. So at the end, everything went all right. All right, back in 3D, because volumes are computed in 3D. So it's very important to test what happens in 3D, because kitchens are multiple migration pathways and timing of values, and many things can happen more on 3D than it did in 2D. So you have two views here in 3D at the well location. On the surface here, you have the transformation ratio around the late Jurassic, and on the section here and the block here, you have the saturation in the sections. Around Great Barrier Way, we have implemented 3D faults into model to account for the result of the 2D kinematic. So even in 3D, with different possible routes, the hydrocarbon did not make it to the well. And in Lona, many of the kitchens, one here, one there, allowing different migration routes, helping to feed the area. But Lona actually is not sitting at the very apex of a structure, but will be somewhere here, a little bit more to the north. So basically, the wells on dry, but for just about a few kilometers, we could have been an actual success. So I propose here a synthetic petroleum chart that illustrates the components that are the timing of generation, the expulsion, the migration, and entrapment of hydrocarbons. So two proven source rock here, the great equivalent and an upper Titanian one, they provide hydrocarbon charge throughout the basin from the end of Jurassic until the present day. They constitute the main prolific system with most of the hydrocarbon. The Cretaceous source rock is there, and it's generating later during the Cenozoic, and expulsion is still ongoing. The possibility of a Chimeridian Oxfordian source rock exists. It's mature to other matures in area and provides additional resources that we put in some of our models. A couple of words on the sealing efficiency, but happens really until the not until the mid-Cretaceous to Cenozoic. So for the highest highs of the highest highs, that makes risks. As we said, with Great Barrier Reef, faults create suitable trapping for hydrocarbons, especially when they are close to source rocks. And something we haven't talked about it, but it's the presence of reservoir in low temperature conditions for longer period of time that allow biodegradation. So this phenomenon has been considered into our resources. Resources, well, resources that can be present in the place according to our equiprobable and calibrated petroleum system scenarios were calculated using Monte Carlo approach from the different scenario-based model. In summary, we evaluated to 15.2 billion oil equivalent barrel to be expected for the most likely scenario. As you see in the distribution here, the low, the most likely, and the high case, they reflect the uncertainties within all equiprobable geological models. Well, we did some risk analysis that was performed for individual leads and at play level, but those results are only private to Nalcor, so no disclosure here. But for each low, most likely, and high case, a probability of geological success is assigned in order to assess the risk volumes. So the estimated probability of geological success to find the P50 estimate is 22%. It means that we estimate at 22% the chance to attain the 50.2 billion barrels. This is a medium to high risk exploration area and compares well with our assessment we've done in Newfoundland, but it also compares well with other places that we've been assessed around the world. So this risk, of course, is directly dependent on the amount and quality of data. And as Paul said, in that area, we have a chance to have fantastic 3D and the sound explanation for the dry well. So all of that brings us a lot of confidence in these numbers. Well, we're reaching about the end of the talk. So what is next? Next is 2021. So we're looking forward to those very exciting new adventures. If you want to know more about what we do in terms of resource assessment, do not hesitate to reach out to us. And thank you very much.
Thank you.